This is checkpoint 1 on gravitational field strength. Okay, here's our first question. We've got a graph about proportionality. So you just need to think clearly here what you know. So this is the gravitational force against the various possibilities of things we might plot to do with the distance away from the source. Well, the equation that we know is F equals G m over r squared. So we can forget all the top of that because this is just about the effect of r. So F is proportional to 1 over r squared. So all we need to do is look for a graph that's got F and 1 over r squared, and that's going to be a proportional line. Okay, so D is the correct answer. Don't be confused, the most common mistake is this one, but of course if you plot F against r squared, that will be an inverse relationship, but that looks something like this, not a straight line. Okay, so this question is about the gravity on different planets. So we start off with the Earth. The Earth's got a radius which we're going to call r and a density rho, and it gives you g. So g is gm over r squared, which in this case we haven't got the mass, we've got a density. So this is g times 4/3 pi r cubed rho divided by r squared. Okay, the quick way to do this is to notice that the r squared cancels out with 2 of those r's there, and we end up with 4/3 g pi r rho. Okay, here's our second planet here with a radius of 2r and a density of 2 rho. Okay, so if we do the same thing of here, our new gravity g dash is 4/3 g pi r dash rho dash, but r dash is 2r and rho dash is 2 rho, so that's 4/3 g pi 2r 2 rho, which is 4 lots of 4/3 g pi r rho, which was our original g, so it's 4g. So the gravity is 4 times the original gravity. Okay, if you want to, if you're clever enough, you can say this. Sorry, that has made it go down by a factor of 4. This has made it go up by a factor of 2, but this has also made it go up by a factor of 8, because doubling the radius makes the volume 8 times as big. So overall we've got up by 2, up by 8, so 16 up, factor of 4 down gives us 4 up overall. Okay, also quite a tricky one, this one. So a small mass is situated between 2 large masses, m1 and m2, such that it experiences no resultant gravitational force, and the distance of mass m1 is r1. So we're somewhere between here, r1 away from this one, r2 away from this one, and the resultant gravity is 0. So the gravitational attraction of this one is gm1 over r1 squared, and then the gravitational attraction of this one is gm2 over r2 squared. Okay, straight away you can see the g's will cancel out. Then you've just got to try and rearrange this to get r1 over r2. So a bit of cross multiplying gives you m1 over m2 equals r1 squared over r2 squared. Okay, you need to take the square root of that to get r1 over r2 is equal to the square root of m1 over m2. Okay, so again you get C. Hopefully you can see that you must be further away from the planet with more mass. So if m1 over m2 is a number bigger than 1, r1 over r2 is going to be a big number bigger than 1. Okay, this is the velocity of the satellite, so be careful here with you looking for v's. So this is F equals g m over r squared equals mv squared over r. So the little m's cancel out straight away, the r's cancel, that r cancels one of those r's, and we get gm over r equals v squared So V equals the square root of gm over r. Only in this case we're at a radius big R and we're at height h above that, so that gives us the square root of gm over r plus h, the whole of that being in the square root sign, which makes it C again. Okay, just a one long answer question on this paper. So we've got a detector, sorry about that scribbling, a detector going on here. It's 68 milliseconds for the microwave signal, so they haven't given us a clue here, but we need to know that microwave signals travel at the speed of light. So this is just the distance equals speed times time calculation. So 3 times 10 to the 8 times 68 times 10 to the minus 3 gives us a height of 2.04 times 10 to the 7 meters. Okay, show the gravitational field strength of this position is about 0.56. So we've got some data. So this is G equals gm over r squared. So that is 6.67 times 10 to the minus 11 times the mass of the Earth, 6.0 times 10 to the 24, divided by, and then the only trap in here is that the r is the 2.04 times 10 to the 7, which we've just worked out was the height from the surface of the Earth, plus the 6.4, again be careful here, times 10 to the 6, or 6,400 times 10 to the 3 squared, and that of course gives you 0.56 newtons per kilogram. Okay, then to work out its speed, okay, you can go back to square one here, but we've just worked out that gravity is 0.56 newtons per kilogram, and of course that is the acceleration, so that gives us the acceleration of something going around in a circle, which is g equals v squared over r. Okay, if you're not quite happy with that, just think back a little bit. This is F equals ma, and this is g m over r squared equals m v squared over r. So you can cancel out the m's there. Gm over r squared is what we just did to get the 0.56, that's v squared over r. Okay, so that gives you v equals the square root of gr, so that's the square root of 0.56 times our number we had before, 2.03 times 10 to the 7 plus 6.4 times 10 to the 6, and that gives you a velocity of 3.9 times 10 to the 3 meters per second. To get the time period, I think the easiest way to do this is to say, well, that's going around in a circle. We've just worked out the radius of this circle is again our 2.03 times 10 to the 7 plus our 6.4 times 10 to the 6. It's going round that, so that's 2 pi r is the distance of the circumference of that, divided by the velocity it's going, which we've just worked out from there. So this is 2 pi times 2.03 times 10 to the 7 plus 6.4 times 10 to the 6, we'll just squeeze that in, divided by 3.9 times 10 to the 3, and that gives you 4.35 times 10 to the 3 seconds. Okay, you can turn that into different units for time if you like. You get about 12 hours.